Can you see my Canvas web page?
Yes.
All right. Let me show you where to go, where to access your Zoom meetings. On the side, there are up to 7 Zoom meetings that are already done, by most of you. If you go to assignment, you will see Zoom meeting 9. Do you see Zoom meeting? Right here. Zoom meeting 11 is the last one we did. You need to go watch the Zoom meeting very carefully and try to understand the concept and question I'm going through at the end of introduction to each topic. So they're going to be Zoom meeting 12. I will add that this afternoon. So that's where you go and access your Zoom meeting. All right, I'm going to go to PowerPoint slides and start describing course material. Let's look at chapter 3. Do you see my PowerPoint slide on chapter 3, chemical bonds?
Yes.
Yes.
All right. Now, the last class period, we gone over, that means the last week. If you haven't come to this, if you haven't watched the Zoom meeting for 11th day Zoom meeting 11, you can go back to the Canvas page and watch it. I gone over in last class Zoom meeting, starting with covalent bond, and I described how Lewis structures are obtained to describe covalent bond. In a Lewis structure, you have octet of electrons. So we gone over that in detail on last Zoom meeting. We also talk about naming binary covalent compounds. How you name binary covalent compounds. For example, CO2 is carbon dioxide. You use prefixes. We also talked about resonance. When more than one Lewis structure is needed to be used to describe the bonding in the molecule, especially then when there's a double bond, which could be found in different bonds that could be redistributed to different bonds. You had to write down several Lewis structures called contributing Lewis structures to describe the properties of the molecule, bond length, where the double bond character is distributed in certain bond of the molecule. So we described that in last class period. We also went over predicting bond angles in covalent molecules. Covalent molecules have molecular structure. That means there's a definite arrangement of covalent bonds around the central atom of the molecule. So we went over valence shell electron pair repulsion theory. So let me briefly revise some of that. Let me go down to where we left off about the VS-EPR theory. Have voice in the... Okay, let me go back to the slide where you have valence shell electron pair repulsion theory. We use valence shell electron pair repulsion theory. I gone over this already in the last class period. If you haven't seen the video, go back and to the Canvasset page and watch it. The idea is based on repulsion of electron pairs around the central atom in a Lewis structure that produce a molecular shape. From the molecular shape, we can tell bond angles between different atoms. For example, methane has tetrahedral structure. There are 4 bonding electron pairs. 4 bonding electron pairs are arranged in tetrahedron. Tetrahedral angle is 109.5. We talked about that last class period. Ammonia has trigonal bipyramidal, triangular bipyramidal, or pyramidal structure. Water has bent or angular structure. There are 4 electron pairs in the Lewis structure, shown here on the top. So you can, 4 electron pair distribution is tetrahedral. 4 electron pairs include 2 lone pairs and 2 bonding electron pairs. They repel each other. So because the lone pairs have greater concentration of electronic charge on the atom, so they repel more. Therefore, 2 bonding electron pairs are reduced from 109 to in tetrahedral arrangement to 104. We talked about that. So in molecules, organic molecules like ethylene, where there's two electron pairs on the carbon atoms in the picture, there's a double bond. Altogether, carbon has 3 electron pairs. When 3 electron pairs are repelled, they produce trigonal planar structure. Therefore, ethylene get a planar structure. I talked in detail in the last class period. Acetylene has 2 electron groups. One CH bonding electron, triple bonding electron between carbon-carbon in the middle. So there are 2 electron pairs around the carbon atom. They repel each other to produce linear bond angle, which is 180. So carbon-hydrogen bond angle is acetylene is. That's how we get the VS-EPR theory. I gone over several problems. You can go back and try to understand the concept if you haven't already watched the video for last class project. Now, this is still about predicting bond angles problems. Trigonal plane has 120. Linear distribution have 180 and 6D. Ammonia has 107. Slight deviation from 109 because of one lone pair of electron. Water has 104 because there are two lone pairs. All right. Today's class, I am going to start with the polarity of covalent bond. All right. Then continue to chapter 4. This is the last topic on the last topic. To predict the polarity of a molecule, whether it's non-polar molecule or polar molecule. Polar means there's a separation of charge distribution. In the molecule, they are going to be they're going to be positively charged area and negative charge area. In a non-polar molecule, charge distribution is even throughout the molecule. Therefore, there's no charge separation. That's the idea. Charge separation or polarity in a molecule comes from polar covalent bonds. Even if molecule has polar covalent bond, they could cancel out through the distribution of bonds in the molecule, creating a non-polar molecule. Therefore, first thing you have to know about what kind of polar bonds can have. Covalent bonds are non-polar covalent bonds when electrons are shared equally. If there is unequal sharing, it's called a polar covalent bond. Unequal sharing comes from electronegativity difference. We have gone over this. Normally, normal covalent bond, non-polar covalent bond is formed when the electronegativity difference is 0.5 to 0 to 0.5. Less than 0.5 means 0 to 0.5. Therefore, if you know the two elements making the bond, you get the electronegativity and subtracted higher electronegativity from the higher low electronegativity, get the electronegativity difference, then you can decide whether it's a non-polar covalent bond or polar covalent bond. If you look at carbon and sulfur, covalent bond between carbon and sulfur, carbon has 2.5 electronegativity of 2.5. Sulfur also has 2.5, therefore electronegativity difference is 0. That covalent bond is non-polar. Therefore, it will not participate in deciding the polarity of the molecule. On the other hand, NH bond is polar. Electronegativity difference is between nitrogen and hydrogen is 0.9. This is in the range 0.5 to 1.9. 0.9 is within this range. Therefore, it's a polar covalent bond. Now we have to decide whether NH dipoles, polar covalent bond produce a dipole, separation of charge, whether they will cancel out or not. OH bond is also polar because 1.4 is between 0.5 and 1.9. So we have to again look at the charge distribution in the how the polar covalent bonds are distributed in the space around the oxygen atom in the water molecule. Between nitrogen and fluorine, if you calculate the electronegativity difference, is 3.1. That is greater than 1.9. When electronegativity difference is greater than 1.9, it's ionic bond. So its ionic bond means there is no molecule. That's a collection of sodium ions and fluoride ions in ionic solid make the ionic compound. Therefore, this polarity, molecular polarity doesn't apply to sodium fluoride, ionic compound. Molecular polarity only, molecular means covalent compounds, only applies to when the molecule has polar covalent bond. Covalent bond is polar. If there's a more electronegative atom and a less electronegative atom. So if you take an example, oxygen and hydrogen, this is (2.5). Oxygen is I forgot the oxygen. Anyway, values are, this is greater electronegativity. That's least electronegative. This bond is polarized towards oxygen atom. And hydrogen has a partial positive charge. This delta negative indicate positive or negative charge on either of these atoms making the bond. Delta plus means least electronegative atom, less electronegative. More electronegative atom has the negative charge. This dipole is represented by the line. The arrowhead is negative end. Arrow tail is positive end. Therefore, you write an arrow like that to represent the polarity or the dipole of the polar bond. For example, another example, chlorine between hydrogen and chlorine, the bond is, the dipole is negative on the chlorine, positive on the hydrogen. This is also represented in the picture here, electron distribution here. Negative is negative end of the dipole is shown in red color. Positive end of the dipole is shown in blue color. You can see there's no equal distribution of charges. That's how you indicate the dipole of HCl. HCl is a polar molecule. A molecule will be polar if it has to have polar covalent bond. Besides, the second criteria is you have to look at the polar bonds and decide whether the polar bonds will cancel each other. So partial negative charge on cancel with the partial positive charge, then molecule become non-polar. Therefore, even if a molecule can have polar covalent bond, it could cancel out. I will give you examples later. For example, example is coming. Carbon dioxide. Carbon dioxide has this structure, Lewis structure. The carbon electronegativity is less than oxygen has more electronegativity than carbon. Therefore, there's a dipole between negative and positive. Negative end. However, these dipoles are oriented opposite to each other equally from at 180 degrees linear arrangement. Therefore, they cancel out. Carbon dioxide, even though it could have polar covalent bond, they cancel out. This is shown in this diagram. What I said. Those two, like in a tug of war, when equal forces are applied, you won't move anywhere. When you at 180 degrees, you pull out with equal forces, it doesn't move. Therefore, polar forces cancel out. Therefore, carbon dioxide molecule is non-polar. In which of the following cases polar covalent bond is formed? When an electron is transferred from one atom to another. When electron transfer takes place, that's not the covalent bond, ionic bond. Therefore, it's not the criteria for polar covalent bond. Electrons bonded are shared equally. That's a non-polar covalent bond. When the electrons of a bond are shared unequally, that's the criteria for polar covalent bond formation. The metallic elements with non-metallic always make ionic compound. Metals have very low electronegativity. Non-metals have high electronegativity. Therefore, they don't make covalent bonds. So it doesn't, polar covalent bond idea doesn't apply to ionic compound. Hence it's C. Which of the Greek letter denotes spatial distribution of charge in a polar bond? We already talked about delta. That should be the answer. Delta is used to indicate the spatial distribution of charge in a polar bond. These are, if you remember from your previous classes, if you have heard about radiation, there are three ionization radiation, alpha, beta, gamma. They don't apply to polar covalent. That's a nuclear property, nuclear decay. So polar covalent bond is electron distribution is indicated by delta. Answer is D. How many electrons are associated with the single covalent bond? That's the idea. Single covalent bond is a dot or two dots or lines. That's a two electrons. Double bond is a four electrons. Therefore, answer is C. Now let's see how the water molecule maintains polarity of the whole molecule. It's a polar molecule. If you look at the water molecule, there are two bonds with polarity pushing out with the negative oxygen as the delta negative. So these two add up, create a negative delta region and positive delta region in the water molecule. Therefore, in water molecule, regions of negative charge and positive charge doesn't cancel out. This is kind of unsymmetrical molecule. Symmetrical means these linear molecules, trigonal pair molecules, or tetrahedral molecules. If you have dipoles arranged in this arrangement, they cancel out. Polar bonds arranged in linear, trigonal planar, or tetrahedral. Water is molecular structure, bent angular molecular structure. The polar covalent bonds doesn't cancel out. In ammonia, same idea. There are three hydrogens with delta positive area. The nitrogen has delta negative. So all these three dipoles added up to a resultant, creating negative area in the molecule close to the nitrogen, and this area, positive area. Therefore, ammonia molecule is a polar molecule. If you look at dichloromethane, that's methane is one carbon atom, and chloroform. To predict the polarity, you have to look at the structure. And also, we're going to look at acidity. So you have to know the molecular structures. You can write down dichloromethane right here, first molecule. In the molecule, there are two polar covalent bonds. Carbon-hydrogen bond is non-polar. Therefore, it's out of the discussion. These two will add up to total polarity as shown here in the molecule. This arrow we talked about, that's the delta negative end, delta positive end. shows total polarity and molecule is polar. If you look at chloroform, the carbon hydrogen bonds are non-polar. You don't look at them. This bond is carbon oxygen double bond is polar. Therefore, total molecule have a charge distribution with delta negative n towards the oxygen and delta positive n towards the bottom half of the molecule. In acetylene, none of these bonds are polar-covalent bond. Carbon-carbon bond is non-polar because electronegativity difference is 0. Carbon-hydrogen bonds are less than 0.5. Therefore, they are considered non-polar. This molecule is non-polar because it doesn't have any polar covalent bond. Characterize the bond that forms between 2.5 carbon and hydrogen. The electronegativity difference is 0.4. 0.4 is less than 0.5. This is 0.0 to 0.5 rate. Therefore, this bond is non-polar. It's less than 0.5. This is 4 here. The answer is B. Between nitrogen and fluorine, electronegativity difference is 1.0. That's the polar covalent bond. A is the correct answer. Between 1 and 3.5, the difference is 0.25. That is greater than 1.9. That's the ionic bond. Answer is D. There are a few more problems. Electronegativity is a concept that is useful along with other concepts. Electronegativity is concept is useful predicting polarity bond. That's true. It is useful in deciding how many electrons are involved in a bond. We cannot tell how many electrons are involved. It only tells attraction of electrons. So it's Lewis structure octet rule, which decides how many electrons are involved in the bond. Octet rule also involves, that's not based on polarity, electronegativity concept. Charge on ion or polyatomic ion is not decided by, it's decided by how many electrons are in the valence shell. The correct answer for that idea, electronegativity, is pretty useful in predicting the polarity of a covalent bond. Which of the following bonds is the bond polarity incorrect? You have to look at the arrow and check out the electronegativity. This is greater electronegativity. Therefore, this is correct. The negative end is on, this is also correct. Potassium has less electronegativity. Magnesium also has less electronegativity than. Therefore, negative end is on a greater electronegativity, hydrogen. That's also correct. In this one, chlorine has higher electronegativity than iodine. Therefore, this is wrong. The electronegativity arrow should be pointed opposite way. Therefore, answer is D. Which bond has the polarity incorrectly labeled? The electronegativity is greater here. I will give you a chart of electronegativities. You can only look at the table and get the numbers. This is incorrect. Electronegativity is oxygen is greater than, I wrote it here, that's wrong. It's greater than, oxygen is greater than carbon. Therefore, this should have been negative. This should have been incorrect label, should be this. This is correct, greater. This is also correct. This is also correct. Therefore, only incorrectly labeled polarities are shown in B. Which of the following bond is the least polar? When you look at halogens, which start from chlorine, bromine, iodine, fluorine, bromine, and iodine, going down the group, electronegativity increases this way. Therefore, iodine has, chlorine has greater electronegativity than iodine. Therefore, this will have the highest polarity, second polarity, third polarity. This will have the least polarity. Answer is D, because the polarity is different. Hydrogen being the first atom in all four cases. Hydrogen iodide has the least polarity. Molecule which of the following is not polar? This is called chloromethane. This is called dichloromethane, carbon tetrachloride. This is called chloroform. If you look at these structures, these are all tetrahedral. Chlorine on the top, hydrogen on the bottom, hydrogen on the bottom. 3 hydrogen. This electronic distribution produce overall polarity of the molecule. There's a polar bond between carbon and chlorine. Therefore, it's polar. We are asking which of the not polar. This is not the answer. This is also polar. We already talked about it. Carbon tetrachloride is a case where all the polar covalent bonds are arranged in a symmetrical arrangement. They cancel out. Therefore, this is non-polar. Chloroform has hydrogen and 3 chlorines. Therefore, it is polar. They add up this way. Carbon-hydrogen bond is not polar. There's a total polarity towards chlorine atoms have negative. Their answer to this question is C. Carbon tetrachloride is non-polar because the polar covalent bonds cancel out in the. Which of the following has the greatest polarity? If you look at this is non-polar, we already talked about carbon-hydrogen bonds are non-polar. Therefore, there's no polarity. That's non-polar. There's no polar covalent bond. This has two polar covalent bonds, but this cancel out in the linear geometry. We already. So this is the only polar bond that should be the greatest polarity. Answer is A. Which of the following molecules is polar? This is, we already gone over, carbon tetrachloride has no polarity. This is a polar. This is non-polar. This is non-polar. Same reason we described here. Therefore, answer is B. Which of the following molecule is polar? When you have molecules like this, this is a organic acid called acetic acid. This group is polar. Therefore, this, when you find organic acid, there it's going to be polar. I wrote it wrong here. HCN also has an electron distribution of like this. Therefore, this bond is non-polar covalent bond. This bond is polar. Therefore, negative N is here. Carbon has less electronegativity than negative. Nitrogen has negative N. This is polar. HCN molecule is polar. Therefore, both of these structures, A and B, therefore answer should be C. Now we finish chapter 3. I am going to go to chapter 4 and start chapter 4. I'm going to stop the share. That's chapter 4. We're going to talk about chemical reaction. We've gone over 3 chapters. Most of the fundamentals that we need to describe chemical reactions are discussed on previous chapters. This chapter will allow us to learn more about chemical reactions. So chemical reactions are equations that we write to. Let me get to the PowerPoint. Chemical reactions are basically chemical equations, where you have reactants and products and an arrow between them. You write the formula of reactants and products, then an arrow representing conversion of reactants to products. Chemical reaction, the reactants change to different chemicals in the products. Therefore, it's a chemical change. Physical change, substance doesn't change. We talked about that. Chemical equation should be balanced. Balancing means atoms of each element on the product side, reactant side should be equal to atoms of the different chemicals formed on the product side. So there are several ways to balance the chemical reaction. We're going to talk about that. Chemical reactions are carried out in solution. Solution is a liquid phase substance. Aqueous solution is water solution. We also use organic compound. We normally don't do gas reaction. They are explosive. Or we don't do solid phase reaction. To make two solid to react, you have to use very high temperature. It's inconvenient and slow. Therefore, we use solution chemistry. Water being the most abundant solvent, we use aqueous solution most of the time. It's cheaper and plenty. We also going to look at different types of chemical reactions. One of the chemical reactions that we are going to look at is redox reaction. This is redox reaction. Redox reaction is oxidation reduction reaction, where electrons are transferred. We're going to look at several types of reaction, including redox reaction, acid-base reaction, precipitation reaction. We're going to talk about them in the section 4.1. After we go over details of chemical reaction, we use chemical reactions to calculate amount of product produced from certain reaction. It's called stoichiometry. In the stoichiometry, use the idea of mole to calculate masses of products produced from the masses of reaction. Mole idea is main idea in the stoichiometry. Chemical equations are based on chemical reactions, which are chemical equations, are based on moles, not from grams. So therefore, when you're doing a chemical reaction, you have to convert grams to moles and do the conversion, then from the moles of product, get the grams of the product back. This is essential part of stoichiometry, calculating mass relationship in chemical reaction. We also can calculate the amount of heat involved in chemical reaction. Heat of reaction is important. We need to know how to calculate amount of heat produced burning certain things. For example, combustion of propane gas, natural gas, etc. I'm not going to talk in detail here about this subtopic under each topic we discussed above. As we do the details in following slides, it will be clear to you. These are the four basic, three types of reactions based on the reactivity, precipitation, acid base. We're going to describe it. Write a balance equation between ion chemical reaction. We also use the solubility rule. I will come back and review later. Now let's talk about chemical reactions. In a chemical reaction, one or more reactants is converted to one or more product. Reactants are found on left side of the chemical reaction, products are found on the right side of the equation. All reactants and products are written in terms of chemical formula of the compounds participating in the reaction. So we discuss 4 aspects of chemical reaction. How to write chemical reaction from the words, names of the compounds converted to formula, and how we balance the chemical reaction. Types of reactions. We already talked about 3 types of reactions. Precipitation, acid-base, redox reaction. We're going to go into detail. Stoichiometry, as I described in the previous slide. Concept of mole is used to convert grams to moles and use the chemical equation to convert reactants to products and obtain finally the grams of products that are produced from certain number of grams of reactants. Heat will be calculated by burning certain grams of reactants. Now let's talk about this. When you look at a chemical reaction, there's a basic pattern that will describe the reaction. The first pattern is 2 compounds come together, sodium and chlorine here, produce sodium chloride. That's called a synthesis. Synthesis means 2 things come together. Decomposition is opposite of synthesis. 1 compound break into 2 simpler compounds. Single displacement is the idea. 1 element, ion, replace copper, and copper is displaced. Single displacement, 1 element is displaced. Double displacement is both components. For example, sodium now goes with sulfate, copper goes with OH, then produce 2 different compounds. That's called the double displacement reaction. You could see in chemical reaction these patterns. Based on reactivity pattern, we already talked about precipitation. Precipitation reactions are when 2 compounds mix in water solution. They produce a precipitate. So you can decide if a precipitation reaction takes place based on solubility rule. We're going to look into that little later. Acid-base reactions are reaction between compounds classified as acid and compound classified as base. When they react, they form water and salt. So these are based on reactivity pattern. Oxidation reduction reactions involve transfer of electron between 2 species in which in the reaction, 1 atom in the atom of element in the product reactant side loses electrons to another atom of element. An electron transfer takes place. These are very important part of reactivity pattern. There are a lot of reactions which can be classified as redox or oxidation reduction reactions. This slide shows summary of chemical reaction based on reactivity pattern. There are 3 major classes. Precipitation, oxidation, reduction, These are called redox also. These are called redox, acid-base reaction. Now, if you look at that, oxidation or redox reactions are these three types. Combustion reaction are also oxidation reaction. When you burn something in oxygen, electrons are transferred from that one of the, for example, carbon to oxygen, carbon dioxide is formed. Therefore, it's basically a electron transfer reaction. Some reactants, beside combustion reaction, some synthesis reaction also involve redox reaction. We're going to look into that. Some decomposition reactions are also redox reaction, oxidation. The Greek letter delta may be written over the reaction arrow in the chemical indicate. Normally, this is the letter on the top of the equation between reactants and products. Indicate the heat. Heat is generated when reaction occurs. That is the answer. Let me look at the choices. The answer is D. Heat is needed. When you write the delta, it means to complete the reaction. Reaction requires heat. That's the correct answer. Catalyst is nothing to do with writing a delta. Heat is generated. That's nothing to do with delta. Heat is needed. That's the answer for that blank. Identify the correct classification for the reaction. This one compound break into two pieces. Simpler compound. Therefore, decomposition. B is the answer. This reaction is two compounds coming into one compound. That's a synthesis reaction. A is the correct answer. As I described, one of the chemical reactions that comes under redox reactions, oxidation reduction, is combustion. There are several types of combustion reactions. One of the common is propane gas. Propane burns in air. Air is oxygen and produce water vapor plus carbon dioxide. So if you look at the reaction here, this is the molecular formula of propane. That's the molecular formula of oxygen, is O2. Products are carbon dioxide and water. This G after the formula is a physical state. That means it's a gas. Sometimes we write liquid if it is a liquid or solid. In solution, we write, solution means aqueous solutions, mainly we write AQ. Now, these are numbers in front of them are right now 1. Like when you write x plus y is equal to 2. Coefficient on the x is 1. Y is here also 1. These are called stoichiometric coefficient. To balance the chemical equation, you need to change them. Stoichiometric coefficient in front of each compound in reactant and product side are used to balance the equation. Now, To know if something is balanced, you count the number of the 3 carbon atoms here. There's only 1 carbon. That's not balanced. You normally change it to 3 here, this stoichiometric, to start with. I'm going to go through some examples, how you change stoichiometric coefficient and make the number of atoms of each element on both sides equal. That's a balancing. If you have a compound like this, there's a 1 calcium here. There's a 1 calcium here. If you look at, there's 2 chlorines here, only 1. You put a 2 here. So that makes 2 hydrogen plus 2 hydrogen, 4 hydrogen on the reactant side, then make a 4 hydrogen here. Then the equation is balanced. Now in the balance equation, coefficients of calcium hydroxide is 1. That's 1 coefficient here, 2 and 2. So this equation is balanced. In photosynthesis, which is a redox reaction, this one is an acid-base reaction. Base plus acid, salt, and water is formed. We talked about acid-base reaction. This is a redox reaction. Oxidation, carbon dioxide with water, this produce glucose, and you can start balancing this equation, writing 6 here, 6. Then there are 12 oxygen and hydrogen atoms. You have to put 6 here. That makes 12 oxygen atoms, 6 oxygen atoms, 18 oxygen atoms. No, 12 oxygen atoms, because the 6 is here. 6 plus 12 is 18. So we will talk about this in detail. We're going to look at how we change the stoichiometric coefficient in the next slide. How do you balance this equation? If the hydrocarbon is even, you normally start with the 2 here. That to avoid complication by producing factors in the stoichiometric coefficient. If you put a 4 here, that's a 8 here. 8 carbons. 2 times 4 is 8. Then the hydrogen should be 5. So if you look at this idea, this is 10, 20. 10 times 2 is 20. This is the correct, this will be 30. You start with and pick up the right one. It cannot be 1. It starts with 2 if it is even. When you look at this equation, you start with the 3 here. 1 here. 2 here. That balances the hydrogen. 12 hydrogen here, 8 hydrogen plus 4 is 12. So answer is in the respiration, they are opposite of photosynthesis. It should be this equation. Balance, this equation is balanced. Respiration is This is opposite. This is photosynthesis. This is something else. It's not respiration. Therefore, answer is respiration is breaking down of glucose with oxygen to carbon dioxide. Idea is you check the atomic balance. D is the correct answer. Ionic compounds are called salts. I am going to stop the class for today. You go back and look at the Zoom meeting which I created. If you need more information, if you have to learn certain topics, if you are not clear about it, you can go back and read it again, listen to it again. All right, I'm going to stop the class for today. Are you guys there?
Yes, sir.
I will see you on next Tuesday.